all of this, the notion of the electric field comes from Coulomb's law. So Coulomb's law is telling you that if I have any two charges, there is a force between them. So why do we, given Coulomb's law, why do we come up with the idea of an electric field? So as I said last time, what Coulomb's law doesn't address is, suppose I have these two charges. Suppose I start with one charge or some charge distribution, and I bring in another charge, okay? How soon will that charge feel the force? Okay, so that is to say, if there is some separation between them, why is it that the new charge should feel a force instantaneously, given that the force is applied over a distance? So we assume that it does feel it instantaneously, so that's one thing that's addressed by the notion of an electric field. Okay, the second related question is, if you do move charges, how soon, how quickly do you get a response? So the idea being that suppose I have a charge here and I'm moving a second charge in the presence of this charge. Okay? If at every point you say that this has to know exactly where this charge is and figure out how soon it reacts to it, then you worry about questions like this. Okay? So you can avoid all these questions by saying, forget the second charge. The very first charge that I have in place alters space everywhere around it. Okay? And if you look at the range of Coulomb's law, what is the range over which two charges feel a force? Okay? In other words, when does this force go to zero? This force only goes to zero when they're infinitely far apart. So as R1, 2, their separation goes to infinity, then there is no force. So it is what's called a long-ranged force. Okay, this is a long-ranged interaction in the sense that it never dies out. Okay, this is what causes a huge headache anytime you have charges involved. Okay, so whether you're talking about the physics inside a cell or you're talking about the mechanism of charge transport across a cell membrane in biology, you have potassium channels, sodium channels, these are all ions that are moving across. The fact that you have an infinite ranged force there can cause huge problems. And you often make it short-ranged by doing things like screening and so on, but to figure out how to apply this, you have to worry about the fact that it acts over all distances. Okay, so if it acts over all distances, then what you say is that if I have a single charge or a collection of charges that are held in place, then they, by their presence, alter space all around them, such that if I bring any other charge in the vicinity of what's already there, I know the effect on that charge. And that effect is immediate because everywhere in space there is a field, a force field due to the first charge. So the point of the electric field is to say that there's some charge distribution. Okay, I don't know what's creating forces, but I know if I were to place a charge Q somewhere in space, it would feel a force due to this charge distribution that's already there. So I can think about the force on Q independent of what that charge distribution is. If I know the effect of that charge distribution everywhere in space, that's the electric field, then I know that the force on charge Q is just going to be Q times the electric field. So another way to say this is to say F on any charge Q is going to be Q times the electric field. So knowing the electric field everywhere in space, anytime I put a charge Q at any point, if I know the electric field at that point, I know immediately the force on charge Q. So by definition, the electric field then is the force on a unit positive test charge. Okay, the second line over here. It's saying it's a force per charge, force per positive charge. Okay, so the units of electric field is force per charge, newtons, which is force units per coulomb, which are charge units.